let's pick up where we left off. So what were we doing last class? You recall that to solve a problem in solid mechanics, we have to satisfy, let's see here, oops, I'm in the wrong spot. We have to satisfy four sets of equations. One which talks about force balances, stress balances, making sure we're in equilibrium. A second which makes sure that the kinematics of the problem are set. If things can't deform somewhere, there needs to be a way of telling the math that the deflection here has to be zero. The deflection here has to be known and it is fixed, or whatever it may be. There has to be a way to ensure that your displacements that you solve for are compatible, they're physically possible. So we've had equilibrium, which talks about how does stress vary, kinematic, which talks about how does strain vary. And in both cases, these are governing differential equations that tell you what's happening in the body, but they also can relate to the boundary conditions being prescribed. For instance, if you apply a force somewhere, you're saying the force here is this, therefore the stress here is this, and that's a boundary condition on these boundary value problems. Kinematic equations, same thing. The strain is going to vary in some way, but sometimes you know things about the strain. For instance, if you are applying a known displacement somewhere, then you have to input that as a boundary condition. Compatibility equations are making sure that our strains are physically possible. And the fourth one kind of ties everything all together. It's our constitutive relations, which is how does stress relate to strain. And we spent a lot of time last class. We started with a 2D element. We calculated what the stress would be at these points. We said as we move some finite distance away, the stress should vary a little bit. How do we figure out how it'll vary? Well, we can Taylor expand our stresses around that point, the origin in this case, such that we have what the stress is plus some change in stress as we move a little bit away. And that's what this is saying. I have your function and I have my change in function to first order as we move away. And equilibrium is defined by these changes in a quantity, in this case stress, to first order. And so what we have is these first order changes, stress in this direction plus a change in stress, stress in this direction plus some change in stress, same with shear as well. And then all we did is the same stuff you've been doing since like sophomore year, is let's calculate equilibrium by doing a force balance. So we summed all the forces. We picked one direction, we picked the x direction. It's a bunch of algebra. You have to take your stresses, multiply it by the area element you have, which in this case was dx, dy, and perhaps into the board, which would be dz. But that's not too bad. You get a stress times an area, and you get a force. Force balance looks like this. With a little bit of simplifying terms here, we reduce this to the equilibrium equations in plane stress. Plane stress is really useful. It doesn't seem like it might be, but there's tons of problems that can be reduced to 2D. You might be wondering why you need to do stuff like that. And the reason is the governing equations of solid mechanics are, as you can see, partial differential equations. But in addition to that, there are also boundary value problems. And boundary value problems are a lot harder than initial value problems. Initial value problems are, you're going to start a pendulum swinging and just try to track how it's moving over time and just following that trajectory, integrating forward in time, seeing where it goes. Boundary value problem is saying, I've got something happening over here. We need to figure out what's happening all the way over here, but we need to make sure that over here we satisfy another condition. Mathematically, that's a lot harder. And so we don't, as I've said numerous times in this class, we don't know really how to handle a lot of PDEs analytically. And what I mean by that is our main tool is, I guess we have a couple. We have separation of variables, which you might have seen if you took a differential equations course. That works sometimes, and it's amazing when it does, but it doesn't work all the time. There are transformations of these equations, things like Laplace transforms, Fourier transforms, in which you're taking these equations and mapping them into a different space to help you solve them in this other space, then you bring them back. But a lot of ways that we end up handling partial differential equations is we try to find a way to make them ordinary differential equations. And that's what we're going to do after we finish going through these equations. Is we're going to have this entire field equations of solid mechanics, and we're going to say, all right, let's solve some problems. The way we will solve them is to try to identify situations in which we can reduce them to ordinary differential equations. We love ordinary differential equations. They have solutions. They have unique solutions, and we know how to solve them. We went from here, and we just kind of extrapolated. Well, there's a pattern here. You have your principal variable, in this case, x, and so you're looking at changes in x with respect to x, y, and perhaps z. And that's what we saw down here. We have kind of x and x paired up, y and y, z and z. And you'll notice that these pink terms stay consistent throughout. That pattern led us to introduce a new type of notation. I don't expect you to be proficient at this level of notation. If you go to graduate school in mechanical engineering, you will spend the first quarter of a continuum mechanics course learning how to handle this notation properly. What I'm doing is showing you it so that way when you see it, you don't think, what are all these i's and j's? You think, oh, wait a minute, I know that has something to do with equilibrium equations. I know there's an approach to unpack this equation to this equation. And the other reason I showed you the compact notation is because you might see it not in this form, but you might see it in this form, which is telling you that your stress is divergence free. So the divergence of your stress is equal to 0. In this case, not technically. In general, what it is your divergence of your stress is equal to the opposite of your body forces, which means if you have some stress distribution in your body, there must be an equilibrium force, body force, kind of counteracting it. To figure out what that body force is, you take the divergence of your stress distribution and you solve for F. And that's what we're going to do right now, to see how to actually use these equations. But the takeaway is this. We have the equations of equilibrium. This is how they look in Cartesian coordinates. So the additional benefit of writing them in this compact notation is not solely to confuse and make you learn a whole new way of writing down mathematical equations. It's because these equations don't say anything about the coordinate system. If you're solving a problem in spherical coordinates or pick your favorite coordinate system, this is still the equation you're solving. Now, as you recall from multivariate calculus, if you're to take the divergence of a vector in polar coordinates, the divergence looks different. You have all those 1 over r df by d theta terms appearing in there. You can either memorize all of these equations in all the different coordinate systems you want, or you can memorize this one equation and then determine what the divergence is in the coordinate system you need it for. More important than that, things like Mathematica will do that for you, or you can say, here's my stress. I know my stress in Cartesian coordinates. Please take the divergence for me in Cartesian coordinates, and it'll spit that out for you. We'll do that in a second. But I first want to set up a problem here. These are the equations of equilibrium. They make sure that all the forces acting on this object are balanced. One of the things that is really important about stress is kind of understanding, that's not how you spell that word, one of the important things about stress is understanding that it's a tensor and understanding what to do with that tensor. That's going to be the primary part of today's lecture. But before we do that, I want to show you how to use the equilibrium equations to solve kind of some kind of trivial mathematical problem. It's not super exciting, but it'll at least give you some practice working with it. And that equation, so what I want us to do is determine if given a stress distribution. So I'm going to give a, let's do an example. So this is what we know. The divergence of stress plus our body force must equal 0. Stress is a tensor. You take the divergence of an object and it takes you down a level from a tensor to a vector. Take the divergence of a vector, you get a scalar. So we take the divergence of a tensor, we get a force. Or sorry, we can take the divergence of a tensor, we get a vector. Force is a vector. The divergence of a tensor is a vector. We can add them up because we're adding like terms. Vector plus vector. Tensor. This operation turns this tensor into a vector. So say you're given a stress distribution. So say your stress tensor looks like this. Maybe you found this by solving some kinematic equations. But let's say we have sigma ij. The sigma xx term is x squared plus 2y. Let's see here. The sigma yy term is xy minus y squared z. And the zz term is x squared minus z squared. Now we need our off-diagonal terms. Sigma xy is going to be negative xy q squared. Let's see. And this one will be 0. It's yz is this one. And xz is not 0. Let's say xz minus zx squared. What? Is that right? Cubed. That can't be right. Let me just double check here. Sorry. Made a mistake here. That's, as I wrote this down, I thought that looks like a z. I hope I don't confuse it. And of course I did. 2x squared y. This tensor, as all stress tensors, is symmetric. So this term is the same as this term. This term is the same as this term. And this term is the same as this term. Symmetric meaning symmetric as upon reflection around the diagonal. So what on earth does this mean? I give you a stress tensor with a bunch of functions in it. Well, think about what we're saying. We're saying that stress can vary in the body, which means that if you pick a point and you're standing in some object, that object is being loaded in some way. You could ask the question, if I walk along the x direction, how does my stress change? If I walk along the y direction, how does it change? If I walk along z, how does that stress change? And that's all this is telling you. It's saying, well, the stress is going to depend, for instance, it's going to, if you walk in the x direction, that stress is going to vary with x squared. And if you have any changes in y linearly, x squared, y. So this is a way of saying, as I move through the body, my stress is going to vary in some complex way with these complex functions. But we don't need to concern ourselves too much with that, because what we know is that equilibrium is dictated by the divergence of this mathematical object. So we could ask the question, given this way that stress varies within the body, what is the body force distribution that ensures that our object is in equilibrium? And what on earth does that mean? It doesn't, it's not as bad as it sounds. What it means is you're given sigma. If we're in equilibrium, there's got to be some body force that balances our stress tensor. So what it's saying is, what's F? And to be precise, we know F is a vector. So really what it's saying is, in Cartesian coordinates, which is what we're in because of our stress distribution, what's Fx, Fy, Fz? If you want to practice how to take partial derivatives of things, you're welcome to do this out by hand. It's not that hard. If you would like to use a mathematical tool like Mathematica to do this for you, that's not too hard either. So I sent you all a Mathematica notebook. If you are able to download it and can open it up, then that could be really helpful. If not, you could open up a blank notebook and you can type in and follow along. I'm going to switch briefly. Oh, actually, I wanted to ask one more question. What's the body force distribution and what's the magnitude of the force vector? Magnitude of your vector, just like always, is the norm of that vector, right? So you take all the components of that vector, you square them, and you take the square root of it. So the norm of F. All right, this is the problem that we're after. I'm going to switch over to Mathematica to show you how you would set this thing up and solve here. So if you want to play along, load up Mathematica and load up the file I sent you. I'm going to kill my kernel and let's switch sharing screens here. This Mathematica notebook I sent you has a bunch of other stuff in there that'll be useful for us throughout the remainder of the semester. For now, you can ignore it. But we'll start up here. It kind of looks like a whole thing. We have stuff on stress, strain, Hooke's law, axisymmetric problems, energy methods, which I kind of separated out to different notebooks to show you. So, okay. I'm gonna close up some things here and try to make this look nicer. Okay, cool. So here we are, Mathematica. what we need to do is, to solve this problem, it's really straightforward. We need to take the divergence of our stress tensor and solve 3 equations simultaneously. The 3 equations are going to be the divergence is going to give us 3 equations, and our unknowns are going to be f of x, f of y, and f of z. In order to do that, we need to tell Mathematica that we have a stress tensor. And so this first little bar here, define a stress tensor, is where we're going to start. I highlighted it in blue. Let me see if I can make this look a little bit nicer. Yeah, that looks better. I'll try to clear it up a little bit here. Okay, so what am I showing you on here? Can everybody see this at home? I think so, right? It's not too small. Here's what we're doing. We're defining sigma. And I said, as you know, with Mathematica, at least a little bit by now, Mathematica handles everything as lists. So a vector is a list, and a tensor is a list of lists. It's not as bad as it sounds. What that basically means is that, so for instance, we need a big list, this big curly bracket on the outside, at the top and the bottom here. And then each row here is top row of my tensor, middle row of my tensor, bottom row of my tensor. And the important thing is that you are telling Mathematica that your stress tensor depends, each component of your stress tensor. So a component of your stress tensor is, one of the entries in this matrix. So here's the XX component of your stress tensor. What we're doing is telling Mathematica that sigma x, I use the shorthand here, I should have probably used sigma xx. Sigma x and sigma xx are kind of used interchangeably. The text I've highlighted there says, hey, our stress tensor has components in the 9 little places there. And each of those components is a function of x, y, and z. And that's what this is saying. It's saying sigma x, the square brackets say this is a function, which means sigma x is a function of x, y, and z. Now remember, our problem, we had sigma x had depended on x and y. It might have depended on z, we don't know. So what we're doing is defining sigma so that each component depends on x, y, and z. So we can run that. And if we want to see what it looks like, we can run this next line, which makes it look kind of like a tensor. Not too bad. We also have to define a body force vector. That's pretty easy. That's just a list. So it's just a vector. F is a list containing f of x, f y, and f z. So that's our body force. Inputting our equilibrium equations is pretty straightforward. Here it is. The thing I highlighted is the math that we wrote down in our notebook. It says the divergence of sigma with respect to x, y, and z. Mathematica will assume we're in Cartesian coordinates unless you tell it otherwise. But you don't have to choose x, y, and z as your coordinates. You could, even if you're in Cartesian coordinates, you could choose whatever you want. A, B, and C, x1, x2, x3, doesn't matter. So you're saying here, hey, I'm taking the divergence with respect to x, y, and z. By default, I didn't say anything else. That means I'm in Cartesian coordinates. And I'm going to add to that divergence my force vector. And now here's where things kind of look awful, but I'll explain this notation to you. So take this, let me highlight the top bar, would. Yeah, sweet, okay. Take this top equation and compare it to the top equation in your notes from last class. It's kind of backwards. So it's going fx plus, and look what it has. It has this kind of awkward notation, sigma x, z, and then it's got up in the exponent kind of 0, 0, 1. And what that is saying is take a partial derivative of that component with respect to x to the 0, so not x, y to the 0, and z to the 1. So it's that line there, this one right here, is telling you take the partial derivative of this quantity with respect to not x, not y, but z. Compare that to your notes. Second term, take the partial derivative of xy with respect to y, take the partial derivative of xx with respect to x. It's a frustrating notation, but we actually don't even care. We don't have to work with this notation because we're not going to be manipulating or playing with these equations. What we're going to be doing is solving a problem with it. So does this notation make sense, at least enough to follow it? If you can, you should be able to map those equations to the equations we wrote in our notebook. So let's do the problem I outlined. You probably don't need to run that one because it should be empty. But here, all I'm doing, unless I made a typo somewhere, is inputting for my stresses the functions that I wrote down in our notebook. Hopefully this is pretty straightforward. Those are just the way you tell it. There's a couple things you might want to be wondering about. I already mentioned this when we went over Introducing Mathematica, but let me just go through it again. These equations are kind of saying sigma x is a function of the stuff in these square brackets. The underscore is basically your way of telling Mathematica, look on the right-hand side of this equation for this variable. So look for x, look for y, look for z. So that's what the underscores mean. This equal sign is basically an equal sign that says, store this, but don't run it yet. Don't run it till I tell you what x, y, and z are. This is like really important if you're, for instance, like if you're defining like a summation in Mathematica, you might say, I'm going to define the summation from n equals 1 to n equals some variable, n to n equals like j or something. And you might say, don't run this thing until I tell you what j is, because you're not going to be able to, how do you run a summation to some unknown thing? So that's all this is saying. It's saying, don't run this until I give you values for this here. Okay, so let's first, very quickly, define our equilibrium equations. Here they are. Here it is again. Divergence of stress with respect to x, y, and z plus f equals 0. Double equal sign here because it's just showing equality. Oops, I never ran these. Three equations result from this equilibrium equation, which we know. We started with three equations. There are three partial differential equations. By giving it functions of x, y, and z for stress, you can calculate those partial derivatives in those three equations. And the outcome is this. These things, each of these equals 0. And so we're left with a pretty simple problem. Three equations, three unknowns. Not too bad. I asked for an arbitrary determine the body force at a particular point. So this is at a point x is equal to negative 0.01, y is equal to 0.03, z is equal to 0.06. And so we can solve for x, we can solve for f of x, fy, and fz at this point by just inserting these values in. So here's what I'm doing. I'm take the divergence, input this stuff for x, y, and z, if I want to find f of x, I just need this first equation. That's what this says. That's what this says. Let me show you. Let me just back up a second. So I can just take, for instance, this. Divergence of my stress plus force at this point equals that thing. And now it's pretty straightforward. I need to now say, hey, take the first one. Oops, wrong way. Take the first one. And solve for, what are we solving for? Solve this equation. When it equals 0 for f of x. Oops. There we go. That's what I wanted. Take the first equation, set it equal to 0, solve for f of x. And that's all we've done in this line here. Take the second equation, set it equal to 0, solve for fy. Take the third equation, set it equal to 0, solve for fz. And here we found what we were asking for, fx, fy, and fz. And we didn't really have to do that much work. We basically asked Mathematica to take the divergence for us. We had 3 equations, 3 unknowns. We solved for them and we're fine. I asked for what the magnitude of the force vector was. Magnitude of the force vector is the square root of fx squared plus fy squared plus fz squared. There we go. And I turned that into something that's in kilograms per meter cubed. So I multiplied it by 1,000. So that's this thing, this ugly mess here. The magnitude of a vector, you should remember this from, I don't know, when did you learn this? Sometime long ago. But sometime at some point in your life, you learned the magnitude of a vector is the norm of that vector, or it's all the components squared, take the square root, and you get the magnitude of that vector. So in Mathematica world, you could just say take the norm of f. Because right, we now know f of x, xy, xz. I never ran these, run them. Now f is a vector with those things, and the norm of that vector is this thing here. So at that point, there's a body force with that magnitude, 68 kilonewtons per meter cubed. The point of this is not to give you some physical intuition for what these body forces mean, or what the how to interpret necessarily like the stress functions that we chose. The point of this is to show you how to work with the equations of equilibrium. It's to say, you've got this kind of awful looking thing, which is a divergence of a tensor. What do you do with that divergence of a tensor? Well, this is what you do. You can, if you know something about your stress distribution, you can calculate the body forces required to keep that in equilibrium. You can do all this out by hand. It's up to you. Questions? No? Okay. we're going to switch gears and then come back to this notebook in a little bit. And we're going to switch gears by talking about stress transformations. One of the challenges with stress is that people generally don't have much of a physical conception for what a tensor is. And you have all of these numbers in there that are hard to interpret. And I say things like a tensor is a matrix, but a matrix isn't necessarily a tensor. And that doesn't really feel satisfying. If you look up any definition of a tensor anywhere, it has a circular definition that when you first hear it is really annoying. And then after you become comfortable with it, it's kind of really profound. And then you're left wondering why there's not a better definition for it. But the definition of a tensor is an object that transforms like a tensor. Which, as the folks at home are missing out on, the folks in class are shaking their heads thinking that's really annoying. So what on earth does that mean? It means that stress is a real thing. Stress is a real thing that will build up in an object when you apply forces to it. And that real thing, just like any other real thing in the universe, should not depend on how you choose to measure it. Meaning, I can arbitrarily put some coordinates on there and call them x, y, and z. And you might arbitrarily choose to pick some coordinates that are totally different than me and put x, y, and z on there. I will measure my stress tensor in my coordinates and get 9 numbers in a box. You will use your coordinate system and get 9 totally different numbers in a box. But those two things are measuring the same physical object, same physical property that's actually happening in response to those forces. How can that be possible? And a tensor is something that transforms like a tensor. It follows certain rules. And those rules are really, really important because what those rules do is they say, okay, well, if you measured it this way and I measured it this way, there must be some way to confirm that we both measured the same object. There must be something intrinsic to the stress tensor that says, no matter how you measure it, we're both measuring the same thing. And so there's two really core essential ideas about handling these objects, these tensors, that they seem when you're introduced to them in mechanics of materials to be kind of like another thing you do, like math-wise, to your stress tensor. But in reality, what it's allowing you to do is, one, be able to measure something in one coordinate system and then transform those measurements to a different coordinate system. That could be for as simple as making sure that we're both measuring the same thing. It could also be because you picked a coordinate system that logically makes a ton of sense. Like for instance, and this is an example you've probably seen before. So for instance, you have a bar like this. It is pretty logical to put your x-axis along the long axis of the structure, to put your y-axis up here, to put your z-axis over here. However, you might be an engineer monitoring the health of a propeller on an airplane, and you kind of know the shape of this object, and you picked your coordinate system that allows you to very easily measure what the forces are as this thing spins around. But then you might notice a crack developing over here. And at that point, it may no longer be of interest to you to know what the stresses are in the x direction, because what you really might want to know is what are the stresses acting normal and parallel to that crack interface. So what are my stresses here at some new x direction and some new y direction? Same if you're doing woodworking and you're taking two pieces of wood and cutting at them at an angle and bonding them together. Maybe you're going to bond that with glue. That glue is going to be meant to resist the shear stress, resist sliding. That's what your glue is doing in that regard. And so if you're trying to determine what the right adhesive to choose is, you need to know what the shear stress is at the angle that you are bonding these two joints together. And so even though your object might be a long beam, if you've cut it at a 45-degree angle and you're mounting them together with some glue, you need to know the shear stress at that angle, which you're not going to get if you have your coordinate system in this configuration. Now, oftentimes it's really easy to calculate your stress tensor with this coordinate system. So for instance, if I apply a force here, a force P, well, it's really easy for me to calculate what the stress is in the x direction. It's just that force over my purple area that I just colored in right there. That's pretty easy for me to determine. It's also really easy for me to tell you that there's no stress in y because there's no force in y, and there's no stress in z because there's no force in z. So in this case, it's really easy to determine the stress in the x direction, but what we really want is the stress in the x prime direction, because that's what's happening at the crack or the adhesive or the weld point. And so what I need to be able to do is to go from this thing to this thing. I need to transform my force, which is a force in the x direction, into a force in the new x direction. We'll call it x prime. I guess I already called it x prime. And we can just do geometry here, right? In 1D, this is really trivial. My force in my new direction is going to be the old force projected into that new direction, which means take that old force times the cosine of that angle. Now, if I'm projecting it into my angle theta, obviously there's got to be another component that's now going to be in my new y direction. You can probably guess what that is. It's going to be the original force times the sine of theta. There's another complication. We want the stress in this direction, which means we need to take the force in this direction, which we have now, and divide it by the area in this direction. Area also changes. You can see it in my drawing. The area of this thing is not the same as the area of my other thing. So we have to transform the area too. So that my area, let's do this different way. Let's do this over here. So that my area in the new plane is going to be my old area divided by that cosine of theta. And in my y direction, of course, divided by sine. And as a result, my new stress in the x direction is going to be my force in that direction over my area in that direction. It's going to be P cos theta over A divided by cos theta. And we get something like the old stress, because this is my old stress that is easy for me to calculate, times the square of the cosine of my angle. If you're interested in glues and welds and such, you're really, as I mentioned, you're interested in what's happening in shear on that surface. That's what's going to resist sliding. Your glue is going to resist sliding there, and so you might want to calculate what the shear stress is. That's going to be your force in the y direction, but your shear stress is the force in the y direction divided by the area in x, right? Because it's parallel. Shear is going to be the force divided by the area that's parallel to that force. So we don't actually need to use a y prime. We use a x prime again. Where's that thing? Why did you sign it? P over A sine theta cosine theta. I think it's because of the y. Check my math on that. I'll check my math on the sign of that, but the takeaway I want you to have is on the right-hand side of this equation. And we're going to do this in a more general way in a moment. But what I want you to see is that the stress in your new configuration is the stress in your old configuration times some function of the angle you've rotated it at. In this case, that function is cosine squared. In this case, that function is sine theta cos theta. This should be familiar. We did this in mechanics of materials. I think there's a cleaner way to do it than we do it in mechanics of materials. That I've never been satisfied by the whole kind of Moore's circle approach to these things. It feels like a bit of an arbitrary, well, to be frank, like a way to calculate stress transformations when computers were not there to help us with these types of things. And so there's a much cleaner way that is much more general for us to use, and it just requires, deep sigh, us to remember some linear algebra. We can do it. And because all we're doing really is rotating a matrix. And we know how to rotate matrices. There is a rotation matrix that is helpful for us to take one quantity and rotate it by an angle theta. gosh. And as we'll see, unlike Moore's circle, with a little bit of help, this one's pretty straightforward to take us from 2D to 3D. In particular, linear algebra solves both of these problems for us. Remember, what are our two problems? One is we want to be able to transform our stress that is maybe easy to calculate in one direction, like we just saw. That was an easy stress to calculate in the XX direction. We calculate it in some direction that's easy for us to do, and then we transform it into a coordinate system that is perhaps more important for us to know. We really want to know the stress acting at an angle, normal or parallel to that angle, but it's easy for us to calculate this other stress. And so we have to transform the stress that's easy for us to calculate to the stress that is acting on the area that we're really interested in. That's what stress transformation is, and we can use rotation matrices from linear algebra to solve this problem for us. The second thing we want gets back to that question of if stress is a real thing occurring in a body in response to forces, just like all of the physical laws in the universe, they should not depend on the orientation of the observer. This question, like Einstein spent years trying to resolve this issue of removing the coordinate frame, removing the observer when developing theories of general relativity. Is this idea that these properties shouldn't depend on your way of looking at them and your way of measuring them. They should be invariant. There should be something about them that doesn't vary as you switch from one coordinate system to the next. And those things that are invariant, they don't vary, are the kind of fundamental intrinsic quantities of these matrices. And what those are also objects that you're familiar with linear algebra. They're the eigenvalues, which are the magnitudes of the principal stresses. Remember, your eigenvalues, once you diagonalize a matrix, you have a matrix that's got a bunch of numbers in it. You do something to it to turn that matrix into a bunch of zeros, except on the diagonals, you have some numbers there. Your eigenvalues are the principal stresses, the stresses along those diagonals. They're very, very important for two reasons. One, they're the invariant thing that allows you to say, I'm measuring it here, you're measuring it here, we're both measuring the same thing. Because if we look at the eigenvalues, they're identical. This is the same object that we're measuring. So the eigenvalues are kind of fundamentally important to ensure that you're measuring something that is intrinsic to this physical object, something that is true, like a property of this physical object in space. But eigenvalues are really important to engineers because looking at a 3x3 stress tensor with 6 unique numbers in it, it is incredibly difficult to discern what is the highest, what is the largest value of stress in this body, and in what direction is it pointing. So going along with your eigenvalues, which tells you what the largest value of stress is, your eigenvectors tell you which direction those stresses are pointing. And so stress transformation, even though it seems like this kind of, I don't know, unnecessary tool for kind of manipulating your stress tensors, it's really doing a couple really important fundamental things for engineers. One is it's allowing you to map what you can measure over here to what you might be interested in a different frame. And two, it tells you what the largest amounts of stress are, which is crucial if you're trying to say, is this thing going to break? It's going to break if the stress in this body exceeds this ultimate stress, which is a material property. How do I know if this loading is generating a stress that will exceed that critical stress? You can't just look at the stress tensor. You need to look at the principal stresses, the eigenvalues of that stress tensor. And if you're saying, okay, I found this stress is actually exceeding my stress, this thing is going to fail, I should reinforce this body somehow to prevent failure in this way. How do I reinforce it? Your eigenvectors tell you which direction this crack is going to form and allow you to reinforce the object accordingly. So our next task is to use linear algebra to do stress transformations. Use linear algebra to calculate our eigenvalues. You've done all this in 2D, so it's going to be a review. Some of you may have seen this in 3D. I don't think so, but we're going to show that the same approach, the benefit of building up this kind of linear algebra machinery here is that stress transformation in 3D is just hard. You can rotate in 3 angles. Like that's not just theta. You're now being able to rotate in kind of this direction, this direction, this direction. 3 angles is tricky. What happens if you're trying to rotate arbitrarily in 3D? However, using the tools from linear algebra, the equations are the same. There's a little bit of extra that goes into it. Same thing is true for calculating the eigenvalues of a 3D stress tensor. Doing that in a kind of more circle way, or as I know is not possible except in kind of pseudo 3D stress states, but it's very straightforward. You use the exact same equations to do it in 3D as you did in 2D. The math is just a little harder. The benefit for us is that we have Mathematica to help us with some of these tedious calculations. So before we dive into the linear algebra and dust off some of your freshman year knowledge, let's take a break until like, say, 10:06. All right. Let's dust off the old linear algebra. It won't be too painful, I promise. Well, can't really make that promise. So, as you may recall from thinking about, it doesn't matter if you recall this or not. There's basically two things you can do. So one is, here's your object. It's a rectangle. And here's your coordinate system. If you would like to know stress at a different angle, you have two options. One is you can rotate the coordinate system. By some angle theta. This is the one that we care about. This is the one that we're always going to do. But just because this might lead to some confusion in thinking back to what you've learned in the past, your other option is you could say, here's my object. Oh gosh, that's not a line. And you could say, you know what, my coordinate system is fixed. Don't change that. Instead, rotate the object. These two different things are very, very similar. They almost seem the same. They produce different rotation matrices. So this one where you're rotating, oh gosh, this one where you're rotating the coordinate system produces a rotation matrix Q, which is cos theta, sine theta, negative sine theta. And this one produces a rotation matrix R, which is the transpose of that. So if you're wondering why we're maybe using a rotation matrix that's not the rotation matrix you remember, we're going to be using this one. This is why. Because it comes down to, are you rotating your reference frame or are you rotating your object in a fixed reference frame? In general, we will always be doing the thing I highlighted, rotating the reference frame, keeping your structure where it is, rotating the frame in which you're measuring things. Once you understand that and you know Q, then you might recall this equation, you might not. If I have a old matrix and I would like to rotate it to a new matrix, my new matrix, sigma prime, is going to be equal to the rotation matrix dotted into my old stress tensor, dotted into the transpose of my rotation matrix. You could choose to remember Moore's circle. You could choose to remember the stress transformation equations in 2D. They're messy. They involve stresses in x and y plus stresses in x times sines of thetas, cosines of thetas. Or for all rotations in 2D and 3D, you can just remember this equation and just know that in 2D, this is Q. And in 3D, we have to think about Q, and we'll talk about how to determine Q for 3D. I think this is pretty powerful. it's pretty straightforward to implement something like this in Mathematica. So let me show you how to do it. I'm going to switch gears here. Switch over to here. Again, this is in the same notebook I sent you. You just need to come down to stress transformation 2D. So that's this thing. And if you open that up, again, I'm going to kill everything. I'm going to quit everything, quit my kernel local. You could also run this top command here, clear global weird symbols. We're going to do this in 2D first because we're working on we already did 1D rotations. We're working on 2D rotations. So we define a 2D stress tensor. Remember, this is kind of like each row. Probably looks better if I write it like that. Sigma x, sigma xy, sigma xy, sigma y. Here's my 2D stress tensor. I called it sigma 2D. And if you like, you can look at what this looks like. Looks like a tensor. I don't think I need to run this, do I? We'll run this. Okay, rotation matrix. Here's us defining the rotation matrix. Again, I'll spread this out so it looks more friendly. I'm defining Q in 2D as just cosine, negative sine, cos. And again, once we define this, we can observe how it looks. It's very straightforward for Mathematica to do a transpose. You either literally type transpose your object, or you can take your object and raise it to t, just like you kind of do in like matrix algebra. So just to show you what it looks like, the transpose is of course just flopping on the diagonal there. So switching that sine and cosine locations. And then just implementing the equation that we just wrote down, the rotated stress in 2D, so my new stress tensor in my new coordinate frame is equal to my rotation matrix dotted into my old stress tensor. In Mathematica, a dot is just literally a dot, period, dotted into the transpose. If you can't see that, there's a little capital T up here. And this thing is a function of two quantities. You need to send it your angle and you need to send it your original stress tensor. Makes sense. How much am I rotating it and what am I rotating? So let's do this. Let's look at sigma xx in the new coordinate system. I doubt you'll remember this, but there's a chance you might remember this from mechanics of materials, what this looks like. If we evaluate this quantity, I get that my new stress tensor in my x direction is cosine squared sine 2 theta times the different components of my old stress tensor. This is where it starts to connect the dots to Moore's circle. Whenever you see like sine squareds and cosine squareds and sine 2 theta, like you're starting to think of, you should think of circles. This is a parametric way to think of a circle. And so remember in Moore's circle land, everything was 2 theta on our angles as you rotate around that circle. And this is why. You can see the 2 theta appear directly in that last term there. So without doing anything, deriving this thing in messy balances and trying to do this out schematically, just by using what we know from linear algebra, we got the 2D rotation matrix. We can pick it whatever coordinate you want. I picked the x direction. What I can do the y, xy, and the, I think this is one is yy. Oops, nope. Oh yeah, that's right. Yeah, there we go. Yeah, these are equivalent. Let me just show you all of these. Oh gosh.
So notice a couple things. Here's the new sigma xx. Here's the new stress here's the stress in the new y direction. And here's the new shear stress. These should be equivalent. And yeah, they are. They're exactly the same. I'm just being slow. Yeah. So this one and this one are still the same. So you end up with 4 quantities.
Only 3 of them are unique.
We did this really quickly. All we had to do is remember Q dot stress dot Q transpose. Done. One of the things that's important, I think, I don't know if this will help you, is I find it really useful to be able to visualize what it is happening when we're rotating a stress state. And so you kind of saw it in that first case in which you had a force acting in the x direction, and then you saw how that stress changed as you rotate that axis all the way around. So we're going to do that. We're going to plot it. So I picked an arbitrary stress state. So here's my stress tensor. I just picked values for sigma xx, sigma xy, sigma xy, and sigma yy. So this is just an arbitrary state of stress. I just picked it randomly. We can see how our state of stress varies as we rotate our coordinate system. And this is what I'm plotting here. So this is the stress. The blue curve is your normal stress. That means it's your sigma xx or sigma yy. Your red curve is your shear stress. No, wait, sorry. Why did I say purple? Let's plot this again. I don't see purple. There we go. Yeah, this is. No, okay, so this is, yeah, okay, sorry, let me try that again. Your blue curve is the stress in your x direction. Your red curve is the stress in your y direction. And this curve, which was supposed to be purple, which looks to be also red, is your shear stress. Now, the way to make sense of this is to first look at the values when theta is equal to 0. They should correspond to what we put in, right? So when the value of theta is 0, this one is, what is that? It's like 47.5, which is pretty close to what we put in. This is 29, yeah, basically 30. And this is negative 6-ish somewhere. Not actually at 0. Oh, there it is. Negative 6.12. So at theta is equal to 0, we found our original stress states. But look what's happening. As we rotate theta, our normal stress in the x direction is decreasing. Our normal stress in the y direction is increasing. And there's a special point that happens. There's a point at which the stress in x is equal to the stress in y. That's this intersection point here. And what do you notice about this graph when these two terms are equal to each other? Yeah, exactly. When your normal stress, when you rotate to an angle such that your normal stresses are equivalent, that corresponds to the angle at which your shear stress is a maximum. So if you just take this dot, so you take this intersection point and just move yourself down, that corresponds to, in this case, a minimum or maximum of your shear stress. So now if we follow our shear stress up, we get to another special point. And we get to this point here, where your shear stress is exactly 0. That's a special point because that point where your shear stress is 0 corresponds to the maximum value of your normal stress. And the minimum in the other direction. So you can see that here. mathematically, if you were to write your stress tensor, what you would find is that the numbers in that stress tensor are changing as you rotate with theta, and you get to some special point at which the shear stresses are exactly zero, and you just have diagonal terms. Those are the principal stresses. That's the principal stress right there. When you've diagonalized your matrix, you only have stress along the diagonal. Your off-diagonal terms are exactly equal to zero. Your off-diagonal terms correspond to your shear stress terms. When they're zero, your normal stresses are a maximum and a minimum. This is how you determine what the principal stresses are in your object. You can keep rotating and you'll have the same thing happen. You get to the point where they intersect again. And this whole like sinusoidal like form of this is why people said, hey, this looks like a circle. I'm just kind of going around in a circle. If I, instead of plotting this with theta, I plot this in and map it onto a circle, I go around in a circle. I go from my maximum and minimum value of my principal stress when my shear stress was zero on Moore's circle, to the maximum of my shear stress when my normal stress was an average. So that's not bad. We would like a more mathematical way to predict or determine what the principal stresses are. We did this using Moore's circle and using kind of geometry. This time we're going to do this using linear algebra. So we want to know these values. These are the important values for us. These are really critically important. What's the maximum stress? That's going to tell you if your object is going to fail. How do we determine those? Those are our eigenvalues. We know how to do this. Let me come back to over here and share my screen again. We have this problem. We have a stress tensor . And we'd like to find this, where, remembering our graph that we were just looking at, oh, I flipped it, didn't I? Forgive my terrible drawing. And then our shear stress ones were in purple. There we go. This is my drawing of the graph we were just looking at. We started here. That corresponds to these values. We'd like to know how to find
these values. These are our principal stresses. Oh gosh. You've done this before, but I'd like to do this a different way now because it's going to make it easier for us to do it in 3D. This is a straightforward problem in linear algebra. It's diagonalizing a matrix. And what we would like to do is take this matrix and get rid of all the off diagonal terms. So there's got to be something that we can take away from these terms here to end up with a diagonalized matrix. And the way we handle this, hopefully it rings a bell for you. It is through taking the determinant of your stress tensor minus some unknown lambda times the identity matrix and setting that determinant equal to 0. What does this thing look like? This looks kind of scary. Okay, well, the identity matrix, so we have here is lambda, which is a scalar, times the identity matrix. This is 1, 1, 0, 0. And so this quantity equals lambda, lambda. This quantity we've already defined. We don't need to define it again. And so this quantity yellow over here becomes sigma xx minus lambda, sigma xy, sigma xy, sigma yy minus lambda. And now we need to take the determinant of that. Taking the determinant of a 2x2 matrix is really easy. You multiply your diagonal term. Ooh, that's terrible. You multiply your diagonal terms by each other, and you subtract the product of your off diagonal terms. So you get something that looks like this. And this equation says take the determinant and set the determinant equal to 0. In 2D, I think it's actually instructive to do this out by hand. We don't need to do it out by hand, but I actually think you can learn something pretty quickly. And so what do we get here? We get, so we're going to do this one out. Let's expand this first term here. I think it's sigma x, x, sigma y, y, minus sigma x, x, lambda, minus sigma, minus lambda, sigma y, y, plus lambda squared. oops, we lost the other term. Minus sigma xy squared. So where I should be more clear, where this term is just this, and the rest of this comes from expanding out the product there. We can now, this algebra I think has some utility to it. So we can now factor lambda here and say, well, this is really like sigma xx we can pull out the negative signs. This becomes negative lambda sigma xx plus sigma yy. And I'm going to move this term over here, just so rearranging it in the equation. So I'm going to say sigma xx sigma yy minus sigma xy squared. Just clean up some of my messiness. Plus lambda squared equals 0. And depending on, we've talked about this in this class, so you can't even blame linear algebra being a long time away. We've already talked about what are the two invariants of a 2x2 matrix when we talked about Gaussian curvature and mean curvature. We talked about what happens when you try to deform a manifold. And the two invariants of a 2x2 matrix are its trace and its determinant. And this is exactly what we find. This is the trace. The trace is the sum of the diagonals. This is the determinant. We just went through the determinant, not hard. So we can call this top one our first invariant, I1, which is the trace of sigma. We can call this thing our second invariant, I2, which is the determinant of sigma. So then we're left with a pretty straightforward quadratic equation. Second invariant minus lambda, first invariant, plus lambda squared equals 0. I do this because in 3D it's less obvious, but the takeaway is still the same. A 2D matrix, therefore a 2D tensor, has two invariants. A 3D matrix or 3D tensor has three invariants. Those invariants are the things that don't change when you rotate your object around. Your principal stresses are the result of this diagonalization. You get this. When you solve these equations, you get these two principal stresses. That tells you what the magnitude of the maximum stress is for your object that's being loaded. The way you find it is through evaluating the things about a tensor that don't change, that don't depend on how you're measuring stuff. And those are referred to as invariants. Invariants are probably among the most important concepts in mathematical physics that were developed over the last 120 years or so. Primarily a contribution from ME309. She is one of the most important mathematicians of the 1900s. And what she found was that anytime there is symmetry, there's a corresponding balance law of nature. Conservation of momentum, conservation of an object as you that is symmetric about translation, that is about rotation. And these things are all connected through their invariants. And Another's theorem, I think Einstein remarks it as one of the essential elements in his development of theories of general relativity, but it's at her work on connecting invariants and symmetries to balance laws shaped the last 120 years development of classical mechanics, quantum electrodynamics, general relativity, pick your flavor of physics. They all come back to what are the physical things that are invariant? And from those invariants, how can we learn things that must balance out? If we know something can't change, we can know something about what must be balanced, whether it's momentum, mass, energy. These concepts are way deeper and way more profound than what we're getting at here. I bring it up just to point out that like there's a lot of richness underneath this. For our sake, what do we care about as engineers? On a day-to-day basis, we mostly care about making sure the thing that we made is not going to break, which means that we have to make sure that we know how much stress our structure is under when we load it, and how that stress compares to the ultimate or failure stress of that material. These quantities tell us that. The way we determine them is using simple tools of linear algebra. What are the invariants of your matrix? Let me show you what this looks like in 2D, and then we'll do the rest of this in 3D next class. So I'll just do this really quickly so you can see it. It's pretty straightforward to implement. Since you've already defined your stress tensor, all you have to do is ask Mathematica. You don't have to do any of the math here. We did it kind of for fun. You just ask Mathematica for your eigenvalues. So what's the eigenvalues of my matrix? Well, let's give it one as an example. Same thing is true for the eigenvectors. The eigenvectors is a messier calculation. You'll notice that we didn't really go through it here, nor did we go through it in mechanics and materials really. Calculating the eigenvalues is a little bit more unpleasant. But it's straightforward to do here. Let's see if this works. I think it'll work. These look awful. There's ways to simplify these, but I haven't done it yet here. You've derived these before, but these are the equations that will tell you what the eigenvalues are, or what the angle is. This is what I said, that the derivation of the eigenvectors is awful. These are the eigenvectors. This is the angle at which the principal stresses are large at. I don't want you to worry about these other than to know that that's why we didn't do the derivation, because it's just kind of a mess. However, it's pretty straightforward to take that matrix that we were using earlier and determine its eigenvalue. So here's our matrix that we used earlier. If we run this, and here are its eigenvalues. Just take our eigenvalues of our function. Remember, OP is the principal stresses. It's just the eigenvalues of sigma. You spit it out, and you get the maximum stresses in this object. And if you go back up and scroll, so what is this? This is like almost 50 and 28. And what you see is, of course, this is this point here. We found that point. This is almost 50. This is like 28. It's hard for me to overstate the importance of these things. I know that they seem kind of abstract, but it really, I just want to kind of reiterate, stress is a real physical quantity like velocity. But it's got this messy 3x3 form for how to store the components of stresses in all the possible directions. And so what we need to be able to do is, one, understand that if we measure stress using one coordinate system, since we're measuring a true thing that is happening, it should not depend on that coordinate system. We should be able to transform that object into another coordinate system, which we're going to get a different components of our stress tensor.
The stress in the body is the same. The components of the stress tensor, the components meaning the stuff that's in the matrix, those change. But the stress that the object is feeling is the same, no matter how you measure it. The components depend on your choice of X, Y, and Z. The stress does not. The second point is it's essential to know, in a practical sense for engineers, where is the stress the largest, and does it exceed some material property that will cause this to break? And those principal stresses are nothing more than the eigenvalues of your stress tensor. We know how to calculate those, and we know how to take those eigenvalues and compare them to material properties and see if our structure is going to fail. I know this seems kind of abstract, but I promise it is. It's an important tool for making sense of what it is we're actually measuring when we measure stress. That's all I have for you today. We'll do this in 3D next class. So it takes a little bit more work because, as I said, there's not just one angle, there's now three. Good luck on the midterm. Try your best, get it to me when you can tomorrow. And see you next week. Thanks, everyone.